Hello everyone. I hope that you're enjoying your first day at the RED. And as Muriel said, I was here, sitting where you are about 7 years ago as a PhD student. And I certainly did enjoy it a lot. But of course, that's not the topic of today's talk. So to get into the subject, I would like to start by asking you one question. Who among you thinks that we should not go to Mars? We meaning humans.
Can you specify the question?
Who thinks that we should not, as humans, go to Mars, like sending people? You're overthinking it. Just raise your hand.
So, to land on Mars.
1, 2, 3, 4. Okay, maybe 5, 6 people. Let's say 10 if people are shy. Well, you are right. We should not go to Mars. We should not go to Mars because one of the most interesting things about Mars is that we might find life there. And if we go, we'll contaminate it. We release millions of microbes every hour. And we won't be able to differentiate between what we brought and what was already there. Plus, there might be life on Mars today. There might be ecosystems. And if we contaminated them, we might destroy them. And it's not just life that we might destroy. There is also the landscapes. Mars is beautiful. And if we go there, we're going to modify it. That's what we do wherever we go. And we're going to deprive future generations of a pristine planet. It's also unethical because people will die or might die. It's very dangerous. People might die on the way there, on site, or after coming back from consequences of radiation. And if they don't die, they might also suffer some serious psychological consequences. Plus, of course, we should not abandon the Earth. And there is this idea which is spreading that some people, mostly rich people, might move to Mars if we're destroying the Earth, which means that it's okay to destroy the Earth. And well, even if we don't go with that mindset, even if we go to explore, there are certainly some problems which would solve on Earth first, like global warming, for instance. So you are right, the ones who raised their hand, we should not go to Mars. Now I'm going to ask you a second question. Who thinks that we should go to Mars? Okay, about the same. There are many people who didn't raise their hands. I don't get it. You're not against. You don't think we should not go to Mars, but you also don't think we should go to Mars. So what's happening? Don't tell me you have a nuanced opinion, right? We're at the age of social media, so against you, in favor of it or against it. There is no maybe or depends. So again, I'm asking my question, who thinks we should go to Mars? Okay, a bit more. Well, you're right. We should go to Mars. We should go to Mars because there is so much we could learn there, including whether or not there is life on Mars. And we won't have the answer to this question before we have sent humans. Robots cannot give a definitive answer to that. And it's, of course, there is a risk of contamination. But frankly speaking, there are basically two options, right? Either life, or terrestrial life, could survive on Mars. And in this case, it's probably already contaminated everything. Because there has been a lot of exchange between the two planets, either naturally or with spacecraft, which was poorly sterilized. Or the other option, terrestrial life cannot survive on Mars, and then there is no risk of contaminating an ecosystem. Then you might still be worried about false positives, about detecting what you brought. But frankly speaking, we study life in the Atacama and in Antarctica, and we're not even wearing spacesuits. Mars is beautiful, yes, and it's true that we might modify it to some extent if we go there. But what's the value of beauty if there is nobody to experience it? And it will be dangerous. People might die, that's true. But when did we become so risk-averse as a society? We don't admire great explorers of the past because they were at home until they felt that they could safely go. We admire them because they did great things in spite of risk to their lives. And we're not abandoning the Earth by going to Mars. That's ridiculous. Nobody really believes that. Even in the worst case of global warming, the Earth would still be much more habitable than Mars. So it's a wrong argument, and nobody really, or at least no reasonable person would say that. And certainly there are problems to solve on Earth. Global warming is an example. But if we wait until we've solved those problems, we'll never go to Mars. There will always be problems to solve. And of course, the young generations and the generations after that will have to solve problems caused by generations before, and to which they contribute as well. We should not forget that. But it cannot be the only thing they do. It cannot be their only goal. I mean, that would be depressing. I think they also have a right to have dreams of their own, to have projects of their own, something that they look forward to, and something that makes the future sound exciting. So yes, we should go to Mars. You might be a little bit confused by this introduction, and I hope you are, because if you're not, it's not serving my point. My point being that when people speak about Mars, they tend to be very dogmatic. There is not a lot of room for nuances. People will tell you that we'd have cities on Mars in 20 years, or that we'll never set a foot there, or that it will be unethical to go to Mars, or that we have a moral duty to go. And I mean, there are reasonable arguments to back up all these claims, but there are also misconceptions and half-truths which are spreading rapidly, which makes it very difficult for people who are not experts in the field to have a reasonable opinion of what is feasible, so what we could do or could not do, and what is desirable, what we should and should not do. And that's difficult for non-experts, including people who have to make practical decisions, like politicians, for instance. And we should counteract that for two main reasons. One, to avoid missing out on the benefits that Mars exploration could indeed bring, so scientific discoveries and inspiration, but also to remediate dangerous misconceptions such as the fact that we can go to Mars if we screw up on Earth. And so to contribute to that, even though to a humble extent, together with Michel Viseau, Kirsi Leto, and Muriel Gargaud, we decided to coordinate the writing of that book, which is tentatively, or rather, the working title is Mars and the Earthlings. And as the subtitle suggests, the goal is to provide a realistic view on Mars exploration and colonization, to speak about what is feasible and what is desirable. And for that, we contacted people from different fields, so scientists in areas like biology or planetology, but also philosophers, economists, lawyers, astronauts, science fiction writers, and we gathered them to discuss what is realistic and what is feasible. That book is expected to come out this year and to be published by Springer, and the goal of that talk was to present the conclusions of this book. But Carmen and I are in a little bit of trouble because the book is not finished, so we don't have conclusions. So thanks for coming. No, instead what we're going to do is just to present some topics of the book, so not everything, but some areas that we've selected and just touch upon them. Yeah. And then if you want to know more, so you will have to get a copy of the book. But before I get into, I would say, the meat of the topic, I would like to set the scene for the story that the book is about. I guess you're all familiar with Mars to some extent, the fourth planet from the Sun. And I guess we can all agree that it's a relatively pleasant planet, at least by solar system standards. I mean, it's not too far, so 225 million kilometers on average, but it can get as close as about 50-something million kilometers. The gravity is mild, about 0.30 AG, so you would not get crushed. And it's not very big. I mean, the diameter is about half of that of the Earth, but the surface without the oceans is about the same. Sorry, the surface of Mars is about the same as the Earth without its ocean. So there is still some room. And the days are about 24 hours and 40 minutes, so a little bit more than on Earth, but I guess we could all use those extra 40 minutes in a day. So it's a relatively mild planet, and it's also very beautiful. I mean, you have skies in shades of red, which turn blue at sunset. You have giant ripples and dunes and dust devils like the one here on the bottom left. And the topography is quite extreme. I mean, you have the highest peak in the solar system, Olympus Mons, which is about 22 kilometers high. And for scale up at this little figure here, where you see it in red and in front some terrestrial mountains, including Mount Everest. And so you see that it's about, well, it's more than twice, almost 3 times as high as Mount Everest. You also have the largest canyon in the solar system. That's here a rendering of Valles Marineris, in which you could easily fit the Grand Canyon. You also have 2 moons in the sky. Most abundantly, maybe Phobos, which is close enough and big enough that you can see it at about the size of roughly 1/3 to 1/2 of our full moon. And it's big enough to see that it's not perfectly round. It's more like a potato-shaped moon, which I find charming somehow. You can see it here. And it orbits quite fast, in about 8 hours. Okay, so you can see it, well, it orbits about 3 times in a Martian day. And pretty much anywhere you are on the planet, pretty much any day, you can see it at least once. And when it shows up for about 4 hours, and it's enough to see it change phase in that time, so to see it become more full or less full. And I guess after this talk, you're planning to eat some good food and drink some border wine, but I suggest that afterwards, you step outside for a moment and look at the moon and imagine what it would be like to stare at Phobos at night in the Martian sky. And then you have Deimos, which is smaller and farther away, but which is still brighter than the brightest star. So it's a very beautiful planet, and again, quite mild by solar system standards, but I will admit that it's a bit uncomfortable compared to the Earth. But the gravity is about 0.38 Gs, as I said, which would be fine for a few days, quite fun even, I would say. But on the long term, there would be some serious consequences for health, which is something that Carmen is going to talk about. We have also extreme temperatures, from about minus 150 degrees Celsius to plus 30 degrees Celsius, even though in my understanding it would not feel the same way as on Earth at these temperatures, among others because the atmosphere is thinner, so you would not dissipate heat the same way, but still quite cold. It has UV at higher fluencies than on Earth, but also at lower wavelengths. You know that on Earth we have UVA, part of UVB. On Mars you have UVA, UVB, and part of UVC, which of course you could block relatively easily with a thin layer of pretty much any layer of, a thin layer of any material. But there is a type of radiation which is more problematic, which is ionizing radiation coming from the sun and other parts of the galaxy, which we protected from on Earth by the magnetic field on the atmosphere, but that reach Mars with high dose rates. And those are much harder to block because they can penetrate deeply into materials. And then we have the thin atmosphere, about 1% of the pressure we have on Earth, which of course you could not breathe, and that makes the planet very dry. So that's the place we're talking about, and there we considered 4 different scenarios. The first one would be a small-scale mission, which could be a crew in orbit, and controlling robots on the ground, but mostly we're thinking of crews on the surface, maybe 6 people there, going most likely with a conjunction class mission. So when the seen from the Earth, Mars, and the Sun are on the same side, and going there on a Hohmann transfer, and then for a total mission of about 1,000 days, including 500 days at the surface. That's our, I would say, main working scenario. We could have considered others. For instance, you can hear about opposition class missions, where you live when Mars and the Sun are on opposite side, and then doing maybe a Venus swing by for a total mission which would be shorter. That could be around 700 days, and then a shorter time on the surface, so about 1 to 3 months. Okay, and so that's something which has been considered, but we consider it much less likely than a conjunction mission, which is why we didn't really base our scenarios on it in the book. Then we consider permanent outposts. So that would be a permanently inhabited research station, but with crews that rotate regularly, a bit like we have in Antarctica, for instance. The third one then is permanent settlements with people who go there who actually are moving to Mars and maybe even having kids there. And the fourth type of scenario is Planet B and terraforming, which is actually 2 scenarios. I mean, they usually are treated together, but you could imagine a Planet B scenario, so people going to Mars because something is going wrong with the Earth, without terraforming, so living in domes, for instance. And you can consider terraforming, so making Mars habitable, as an experiment, so not to move there. So they're not really the same scenario, but we put them in the same category, mostly. So we consider those 4 different scenarios, and for each of them we look at what is desirable, again, and what is feasible. And one important aspect of that is, what are we doing there for? What are we going there for? What are we going to do? And I'm going to touch upon that for the first scenario, for a small-scale mission, even though very briefly. So if we look at things objectively, the most likely driver for this type of mission will be politics. And that might sound a bit unelegant, but it's not necessarily a bad thing. And it might be competition. It might be different groups of nations, led, for instance, by the US and by China, competing to go there. But there could also be a joint cooperative agreement between those nations to set a highly visible goal in the frame of a change in world politics. And I know it may sound a bit hard to imagine today, but things might change. Whether or not that is the case, and whether or not politics is indeed the main driver, the main activity on Mars will likely be science. Now, there are many things we could do. I mean, we have an entire planet to explore, but we'll have a limited number of people on site, and they'll be there for a limited time, so we have to set priorities. And in fact, different institutions have proposed some objectives for small-scale, early missions to Mars, and they are quite consensual. So different institutions can have different priorities, but generally the goals are more or less the same, and they tend to fall into three main overarching questions. The first one would be the search for life, which I would argue is the most interesting. I might be a little bit biased because I'm a biologist, but I guess most of you are astrobiologists, so I guess it's a safe opinion to voice here. Although it might sound a bit surprising to look for life on this planet, which as we saw is a little bit hostile. But the reason why there is hope is that Mars has not always been like that. When we think that in the Noachian, about 3.7 to 4.1 billion years ago, Mars had a thick atmosphere, and we don't really know whether it was mostly wet and warm or if it was mostly cold and icy, but there were at least some periods of time when there was liquid water. So it's not completely far-fetched to imagine that there could have been life on Mars at that time. And if that is true, we might be able to detect remnants of it today and to find out that it has a common origin with life on Earth, or perhaps that it has a different origin, most of which could be very interesting, of course. And then after that, something changed in the core of Mars, and it lost its magnetic field, so it's lost its radiation protection. So the atmosphere was stripped by radiation, so the pressure went down, the liquid water was not stable, and so on, which led to the planet we know today. But it is possible that life continued to exist in some habitats, which could be small niches or larger habitats, most likely in the subsurface. So it is not impossible that we'll find life on Mars, which is still active today. Another overarching question would be about the processes that govern the weather and climate on Mars, so now and throughout the history of Mars. And weather largely pertains to atmospheric processes. And for that we can learn a lot by orbit observation, but also from measurement on the ground. On Earth, both complement each other nicely. We expect it to be the same on Mars. We already gather both kind of data on Mars. And that is interesting from a fundamental standpoint, just for the beauty of understanding how it works. But there are also some applied aspects of it. It might help us land spacecraft more accurately on Mars and also develop some forecasting system for future astronaut operations. And then, very briefly, another overarching question is about the processes that shape the surface and the interior of Mars. And I find the surface particularly interesting because you know that on Earth we lost a part of the geological record because of plate tectonics. We're missing about 1 billion years roughly. On Mars, you have a different tectonic system, basically one big plate, and so the geological record is much better preserved. And by studying it, we could learn a lot about Mars, but also about the history of the early Earth. And then we have the core, so the crust, the mantle, and the core. So the interior, so the crust, mantle, and the core, and that is very interesting to planetologists, for instance. So there is a lot of things that we could learn on Mars. We could make very fascinating scientific discoveries at a very high pace, and humans on site could contribute a lot to that, provided, of course, that we can keep them alive. And that's something that Carmen is going to talk about.
My part of the book is not so much about whether we should go to Mars or not, but it's more about answering the question whether we ever will go to Mars, so whether we as humans are actually able to go or whether it's impossible. And of course, I think to be able to answer that question, we actually have to take a step back and consider what we actually know about the human body in space and how it's affected by microgravity, but also partial gravity. So let's look at whether we actually know enough today to be able to answer the question whether we can go to Mars or not. This is Valery Polyakov, and he is very famous in spaceflight. Do any of you know what for? He holds a record. Valery Polyakov holds the record for the longest continuous time spent in space. He spent 437 days on Mir station in the 90s, and this is actually him looking out of Mir to one of a Soyuz capsule coming with some fellow crew members. So 437 days is the longest time any human has ever spent in space continuously. Now a Mars mission, as we learned from Cyprien, will be about 1,000 days. If you look at other people, anybody else who spent a long time in space, we have another cosmonaut who spent about a year in space. Then we have two teams of 2 people, also about a year. The first woman on that list is Christina Koch, who is the only woman who spent more than 300 days in space, and she will also be the first woman orbiting the moon, hopefully next year on the next Artemis mission. And then there's another cosmonaut in that list, and those are all people that have ever been in space more than 300 days. And importantly to know, those missions were not designed to look at whether humans can survive a flight to Mars and back. Those missions were there for various reasons, except for the one of Scott Kelly maybe. He's one of the famous NASA twin study participants. So he spent a year in space while his identical twin spent a year on Earth, and they compared mostly physiological changes afterwards. It's quite an interesting study if you want to read that one. So all the other studies were done for different reasons. And as you can see also from the years on the right side, there's more than 30 years between the first long-term mission and the most recent one. So also, well, devices we measure physiological things with have changed. The issues we look at have changed over those 30 years. So we have data from those 8 people, but it's not something we can really compare. It's not really something we can put together into one analysis and say, okay, those things change and these are the things we must be careful if we go to Mars. So it's from this really difficult to say whether those 1,000 days are possible or not. We have to be considering what we want to do with that Mars mission. So what kind of mission we are talking about. Do we simply go to Mars to plant a flag and come back again? So are we doing those 1,000 days? Or are we talking about building up a permanent science base, as also Cyprien explained earlier, where people maybe spend 1 or 2 or 3 years with the goal of actually afterwards coming back to Earth? Or are we talking about a permanent settlement where people get pregnant, where they raise kids, where they age on Mars? Because the physiological changes we are looking at are very different for each of those missions. And the things we need to consider, the countermeasures we want to apply are very, very different. In addition to that, of course, these 1,000 days are not going to be spent entirely in space, in microgravity. But we also have this stretch of time of the mission that we will spend on Mars, so in partial gravity. Do you know how much time humanity has spent in total in partial gravity, so on the moon? Anybody has a guess? Yeah, that's pretty good. It was a bit more than 12 days, so just under 2 weeks in total. So 12 men on the moon, just under 2 weeks of data of what it's like to live in partial gravity. And of course, those missions were not at all designed to look at physiological changes. So we don't have a lot of data on that at all, sadly. And I will come back to this because this partial gravity thing is actually something that's a big mystery still with anything considering physiology. So this is a picture of a textbook that's by now can be said is quite old. And it's basically a summary of things that change with human physiology and psychology once you go to space. And I say it's old because the textbook is quite some decades old by now, and you can see there's a lot going on. But this was basically pre-ISS data. So for more than 20 years now, we've been collecting physiological data of astronauts going to the ISS, mostly 2-week to 6-month missions. And since then, we've collected so many more issues that we need to be careful about, that if I would add them all to this astronaut, you wouldn't see the guy anymore, which would probably be good. But let's do a thought experiment, and let's say we are launching a group of astronauts to Mars. What is the first thing that will happen to them once they reach microgravity? How would they feel?
Nauseous,
Yeah? Yeah? Why?
because of the internal, how is it called?
The balance?
Mal de mer.
Oh, yeah, yeah. So it's something that's actually quite similar to seasickness, we can say that, or motion sickness. And we call it the space adaptation syndrome. It's basically the astronaut in need of getting adapted to this new environment. And it comes from the fact that your balance system and your visual sense and your tactile receptors, so what you're feeling, it doesn't correspond anymore. And that makes you very confused. And it can, well, over 70% of our astronauts are affected by this. There is a wide array of different symptoms. It can be just a minor discomfort, so you feel nauseated, you feel dizzy, you feel very, very tired, but it can also lead to total incapacitation, so people who can't stop vomiting. And we can't predict on Earth who will be affected and who won't. And apparently, having been on a previous space flight, people are very divided on this, but apparently it doesn't help. So you can be totally fine at your first spaceflight, and at the second one, you can be affected for 5 days and completely unable to work. And this is quite important because it's an adaptation process, right? So once you have passed those 5 days, you're adapted to space. But when you're going to Mars, after 6 to 7 to 8 months, you're going to land on the planet and you're going to be subjected to gravity again, even if it's just partial gravity. But you will need to get adapted to that new environment again. So it's quite likely you will go through the same thing again. And that's in the first 3 to 5 days after landing on Mars. So this is a time where potentially you might have to perform mission critical tasks, but you might also spend this time vomiting in the spaceship. So this is really something we need to consider, because then once you go back to Earth, you launch into microgravity, you're going to have the same thing again, and then landing on Earth once more. So it's not negligible. The second thing that is going to happen, what's the second physiological system that you notice is changing?
Blood circulation.
Yeah, perfect. The cardiovascular system, so your heart, your vessels, your blood flow inside your body, that's the next thing that changes really, really fast. And that's because we are perfectly adapted, of course, to life on Earth, especially our cardiovascular system, the anatomy of the heart, all the way the vessels are looking, everything is just perfect for Earth. And as you can see with this little figure here, while I'm standing upright on Earth, I have this huge gravitational vector going from my head to my feet, meaning that the pressure inside my brain is actually less than the pressure inside my feet, because on top of my feet, of course, we have all this hydrostatic column, all this weight of my body sitting on top. So pressure in the head less than pressure in the feet. And that's important to remember. But once I lie down on Earth, once I lie horizontally, I don't have this big gravitational vector anymore, this head to toe thing. The only thing I have now is this chest to back vector, and that's a tiny one. We can almost ignore it. And what changed as well is that now the pressure inside my body is almost equal everywhere. And that's actually really important to stay healthy on Earth, is to have this stress recovery cycle. So this fact that I am upright for about 16 hours a day, and then I go to sleep and I lie supine for about 8 hours. That's really important, especially for the brain, to have these phases of less pressure, more pressure. The brain really likes that. So spending a weekend in bed is actually probably not so good for brain health. Now, as I'm standing up right now, gravity is pulling blood down towards my feet. And so basically out of the heart towards my feet. But of course it has to come back up again, and luckily our veins, so the vessels that bring blood back to the heart, they're perfectly equipped for that. They have these little valves, or things that look like trapdoors, that basically close as soon as blood tries to flow into the wrong direction. Plus we have those big leg muscles that push blood back up towards the heart. That's a really good system. And then, of course, our heart has to work quite hard in order to bring blood up to the brain, because that's quite a long distance, quite a pressure difference that it has to overcome in order to supply the brain with blood. And humans are actually really weird mammals in that sense that most mammals, if you think about, I don't know, a bear or a cat, they have their heart approximately the same height as their brain. And that's a protective thing that nature protects them with, because the brain, of course, is the organ in our body that needs most oxygen. About 20% of everything that you're breathing in right now goes straight to the brain. And the brain doesn't have any capacity to store oxygen, so as soon as you deprive it of it, it will shut down. That's also the case, for example, if you don't manage to get enough blood to the brain anymore, your body will protect you by fainting, so by having a syncope, basically. Because once you faint, you're supine again, and there it's easier for the heart to supply the brain with blood. And we call this orthostatic intolerance if you're not able to stand upright by yourself, and the fainting process is basically how your body protects yourself. Now, this is a very elegant system all in all, and it's perfectly adapted to life on Earth. But we have a problem with the whole thing once we go to space. Once we go to space, of course, there's nothing pulling blood down anymore. So for our astronaut, it means that all the blood volume that was previously in their legs, that's 1 to 2 liters of blood, now comes to the upper part of the body and settles somewhere in the upper torso and the head. Do you know how much blood volume a normal human has, approximately? Yeah. Yeah, depending on your fitness and your body size, it's 4.5 to 6 liters of blood. So 1 to 2 liters, this basically coming from my legs into my upper body is a huge deal. It's a huge amount of plus. And yeah, imagine those arrows on the upper part of this guy. You have pressure receptors in the vessels in the heart, in the neck, and in the brain. And these receptors, they basically notice when the vessels get too big, when they dilate a lot. And of course, now they are dilating because you have 2 liters too much in this part of the body. And the body notices this, but it doesn't know that it's missing in the legs. So it starts reducing blood volume. And astronauts, they lose between 12 to 20% of their blood volume within the first few weeks in space. And it's completely fine as long as you stay in space. Because of course you don't really need the blood in your legs because you're not moving the legs. You're not using the muscles that much. You don't really need the bones at all. So it's fine to have less volume. Plus the fact that you don't have this hydrostatic column anymore here means that the heart has to work a lot less hard to get blood up to the brain. But the heart is a muscle as well, and muscles you don't exercise, they kind of get weaker. So that's also what potentially would happen in space. You would have less blood volume and a weaker heart. And it's fine in space, as I said, but it's a problem once you land on a planet. So in theory, if you do no countermeasures at all, and then you land back on, you land on Mars, now you have 20% less volume and you have a weaker heart. And once again, those 1 to 2 liters are going to be pulled down into your legs by gravity. And now the heart is possibly not able anymore to supply the brain with the little volume that is left. And therefore, the risk is high that you would faint. This is also why there's quite some little movies of early spaceflight eras where astronauts returned from just a 2-week mission with a space shuttle and they fainted afterwards at the press conference. Nowadays, we try to avoid this by, if you look at the astronauts coming back nowadays, they get transported off in a comfy seat. They get welcomed by a committee of flight surgeons, and the first thing they receive is an infusion of plasma volume to fill up everything they've lost, just in order to make them feel good and make them able to walk. And this is fine on Earth, but of course on Mars they will not have anybody waiting for them there. They will need to perform those mission-critical tasks, and they might suffer from Mars adaptation syndrome, plus this cardiovascular problem. So you see, it's not really that easy. Another thing that will adjust to space, but a bit more gradually, is muscles and bones. So your muscles, your bones, your tendons and ligaments, they're all part of this use it or lose it principle. And for muscles, I think it's quite intuitive, right? If you don't exercise them, you lose them. They get weaker, they get less in mass, and the power is decreasing, so the strength is decreasing. With bones, it's a little bit different. How do I exercise my bones? Any ideas? What keeps a bone healthy?
I was going to say drinking milk.
Yes, but not if you just do that, it won't help you.
Blood supply?
Yeah, but the bone needs an incentive in order to keep dense.
So shocks and vibrations.
Yeah, it's basically so every time bones need biomechanical loading, which is a fancy word for simply impacts, right? So every time I step here, every time I run, if I run uphill or downhill, every time my foot touches the ground, there's this shock wave, a tiny shock wave traveling through my body. And that's basically what's telling the bone to get denser, because the bone realizes, okay, there's some stress here. We need to, get dense. We need to get stronger in order to stay alive. And this is all fine again on Earth, but in space, of course, we're not at all walking. We don't have any kind of shocks unless we maybe crash into the side of the ISS. But so there's really no incentive for the bone to keep dense, because actually keeping bones dense is something that takes a lot of energy. And the body doesn't like to waste energy. So this is also why the muscles decrease. The mass of the muscles decreases as soon as we don't use them, because the body thinks, okay, I'm taking energy to keep up this enormous leg muscles, but we're not walking, so we don't need them. So the muscle mass decreases. But the same is also true for the bones, especially for the big leg bones and the hip bones. So those decrease in density, and actually how much they decrease is extremely individual. So some astronauts lose 0.2% and others lose 2% per month. And that's an enormous amount, especially if you consider that a 3-year Mars mission, that's a lot of months. If you lose 2% per month, you're going to have a problem quite soon. Plus, the thing with bones is that the problem is that what you're losing is minerals, basically, and most of it is calcium. And calcium is also responsible for other biochemical processes, especially in the heart and in the brain. So losing too much calcium from the bone can actually have effects on your heart and on your brain. But because of this, the blood levels of calcium are extremely tightly regulated. So that means as soon as there's a tiny bit too much, it gets eliminated. And that's the next problem, because it gets eliminated via the kidneys. And calcium, too much calcium in the kidneys, has a tendency to form stones. So that's quite out of focus. So it has a tendency to form stones, and these can then obstruct either the kidney itself, or the urethra, or the bladder, or really anything of the way out of the body. And that is excruciatingly painful, a kidney stone. And it's not only painful, but it's also really dangerous, because it can create an infection of the kidney, and an infection of the kidney has a tendency to spread through the whole body and potentially can cause sepsis, and that would be life-threatening. Now, this is really something we do not want on the way to Mars. Sometimes, if the stones are small, you can eliminate them via urine. But if they are too big, worst case scenario, you need to remove them surgically. And doing surgery in space is another of those things that is really not very easy, and we really don't have any idea of how it would work. So this is really something we need to avoid. But it's also a perfect example of how you have one thing changing in space. You have, bones losing density, and you think, okay, risk for fracture goes up. But you also have to think one step further. You have to think about the heart and the brain and what calcium is actually doing. And then you have to think one step further. You have to think about how calcium is eliminated. So it's really not just one issue, but it just brings with it so many more new challenges. It's yeah, it's getting really complicated. The more we know about the body in space, the more complicated it gets. One thing that we can do against all of those things, so the countermeasure astronauts are currently doing, one thing this is doing, we are doing to prevent it is exercise, of course. Astronauts on the ISS, depending if you're a cosmonaut or an astronaut, you're doing exercise 2 hours a day, 5 or 6 days a week. 1 hour of this is in the strength training, so we have picture number 1 and picture number 4. This is the RED. It's a huge device to exercise your muscles, basically. You can do squats, you can do pull-ups, push-ups, whatever is on the schedule that day. And this is basically 1 hour of your day as an astronaut. The other hour of exercise is either on the bike, as you can see on the top right there, or on the treadmill. This would be on the bottom left, and you can see this astronaut, she's wearing a harness, and with this harness you can strap yourself down onto the treadmill with up to 70% of your own body weight, and then basically, so like this you can run in space. Running in space is a bit a tricky thing, because of course a treadmill, building a treadmill inside a space station is not so easy, because it can make vibrations. There's actually an ESA astronaut up for his first time on the ISS, and he's quite a big muscular guy, and he really liked running. So first time exercising in space, he went on the treadmill and he ran. And mission control called him afterwards, saying that, well, you know, either you adjust your running style or you cannot use the treadmill anymore. Because he was just, his steps were so heavy that the whole station was vibrating while he was running. So he had to learn to run a bit lighter. Which of those things is, I mean, I already said it, I think, but only one of those things is good for bones, bone health. The running, yeah, exactly. And that's important because the treadmill is unfortunately quite big as well and quite complicated to implement. And if we're looking at going to Mars or going to the moon, we will not be able to take all 3 of those devices with us. The ISS is a huge station. It's enormous in volume. And RED, as you can see on the bottom, that's a huge device. It's really, really big. And so is the bike, and so is the treadmill. So we will not take all 3 of those things with us on the way to Mars. We really need to find something that's small enough but efficient enough in order to keep our astronauts healthy. Also for the moon, for example, the Gateway station, it's going to be really, really small, more like a student apartment. Than this huge family bed, 5 family members bedroom apartment. And they are really struggling to find something that actually fits into Gateway in order to keep astronauts healthy while orbiting the moon. It's actually ESA who is at the moment trying to find something. They're thinking about biking or maybe jumping. But of course, first you need to try out what actually works. And for 20 years now, our astronauts have always been performing those 2 hours of exercise, and they are relatively fine with it. The big muscle groups can be exercised, and the heart is actually quite well exercised with this bike and treadmill thing. But now they're trying to find some astronauts who voluntarily want to reduce their exercise volume or only bike and do nothing else, in order to see whether that would be enough as well, but they're not finding volunteers for that yet. Because I guess it's also nice to just, as a countermeasure to stress, or to just spend some time doing something else. So it's, some people really like working out in space, apparently. One other thing that we've discovered quite recently, so with ISS data, is that there have been more and more tales of astronauts losing their vision in space. So basically they've been telling mission control that they get farsighted. They see worse and worse. So an astronaut nowadays going on a long-term mission to the ISS, they will have in their luggage an array of different glasses depending on, because we never know what diopters they end up needing. So they take, I don't know, 10 different kind of glasses with them in order to be safe for whatever they end up needing. And well, for about 10 years now, we've been looking at this phenomenon, and we've been looking at the anatomy of the eye, whether there's anything weird. And this is an MRI image of an eyeball, a normal one. And if you look at the one to the right, that's an astronaut coming back from space, and you can see that the eyeball, the back of the eyeball, is actually flatter than it was before. And then we have a picture of the background of the eye. You can see this white spot there, that's the optical nerve, and that's a normal one. And then here, we have those weirdo horizontal stripes at the back of the eye. And that's the choroid. So it's a tissue that's behind the eyeball. And usually this is a really, really nice and flat kind of tissue. It's what supplies the eye with blood. But in space, what this thing is doing is that it's making folds. So it's not flat anymore, but it's kind of wrinkly. And that's probably really, really bad. But we don't know yet what it's doing. And we don't know why this is happening, which is a bit more worrisome. So there are several theories why this could be happening. There are several more changes in eye anatomy. And it might be because we don't have, as I mentioned before, on Earth we have this constant change. We have less pressure in the brain when we are standing upright. We have more pressure in the brain when we are lying supine. And in space we don't have this anymore. In space we probably always have equal pressures throughout the body. And therefore pressure in the brain might be a little bit higher than it is on Earth if we look at a 24-hour mean value. And this tiny bit elevated pressure might be enough for the brain to kind of press on the back of the eyeball and make it just a tiny bit flatter. And that might already be enough for the eyeball, well, for the eye itself to lose its vision. And at the moment, this is not so bad. They lose a few diopters, they put on glasses, they're fine. But the question is, if we're going to Mars for a 1,000-day mission, is this going to keep progressing? Is this going to get worse and worse? And are the astronauts at some point going to go blind? So that's really a question we need to answer before we go in preference. So there's a lot of research going into this at the moment, and especially into the mechanisms behind, but also into what we can do against that thing. Now, there are a lot of more things that are really important on the way to Mars that are kind of beyond the scope of this talk, but we can talk about it in the evenings if you feel like tackling any of those. Now let's say that our group of astronauts, they have arrived on Mars. And worst case scenario, if we don't have the right countermeasures, what is going to happen is they arrive on Mars, they have a weak heart, they have they have brittle bones, they have less muscle mass and strength, their coordination is probably off, there might be changes in brain anatomy, because if there's something happening to the eyes because of high brain pressure, there's probably also something happening within the brain because of this pressure. Their eyesight is bad, their cognitive functions might be off. We are not sure about this yet. I would like to know about this. And they might have orthostatic intolerance. And in addition to that, they're now going to have mass adaptation syndrome. So worst case, we might have an astronaut stepping onto Mars, falling because of this orthostatic intolerance, because the heart doesn't manage to get the blood up there. Then they have brittle bones, so they might actually fracture their bone or strain their muscle and not see where they are falling to, instead of giving us an inspirational quote. So this is something we really need to avoid, and that's why it's so important to do more research on humans, on physiology, on long-term missions in microgravity, but also in partial gravity. But this is really the worst case scenario. So if they actually take a RED and the bike and the treadmill, this is probably not going to happen, probably. But now let's talk quickly about the actual stay on Mars and whether this would be enough for astronauts to keep healthy. And I have this nice little figure where on the y-axis you can see different levels of gravity. And then on the bottom you have anything from poor health, so this would be the ISS without any countermeasures, to optimal health. And we generally assume that our 1G on Earth is optimal health. And a lot of people assume that there is a linear relationship between moon Mars and Earth gravity. So basically that gravity on the moon is almost as detrimental as microgravity, and that gravity on Mars is somewhere in between, not really as bad, but also not really good enough to keep us healthy. But we really don't know, because as I said, we have less than 2 weeks of data from people on the moon. We have nothing from Mars. There were some parabolic flights who are done in lunar and Martian gravity, but parabolic flights give us 22 seconds of microgravity, so they don't really tell us about long-term adaptation. So it's actually also possible that this is not at all a linear relationship, but that Moon and Martian gravity is not enough at all, that we will keep having to exercise 2 hours a day while we are on Mars, just in able to keep fit, just to not lose muscle mass and heart power. But the opposite is also possible. It's possible that actually all we need is a tiny, tiny, tiny bit of gravity, and we're going to stay healthy. That actually the moon will be completely fine, and Mars will even be perfect for our health. And then also there is this possibility that actually Earth is a bit too much for us. Because we all know that with age, our muscles get weaker, our bones get brittle, our heart has a harder time pushing blood up there, we feel dizzy, and our spines kind of tend to bend towards the center of the planet. So it's actually quite possible that life in a planet with 0.6 or 0.7 G would be much healthier for us. And that actually living on Mars in Martian gravity would give us healthier and longer lifespans than we have on Earth. I think it's just I stole this from this book down there. It's a really nice book about space exploration in general. And I think it's a very nice thought experiment to look at it this way. And now let's quickly talk about the permanent settlement still. Let's talk about the fact that people might try to get pregnant and have kids and age on Mars. And that, of course, puts us in front of a whole new level of challenges to the human body than we had before. Already just the trying to get pregnant will be a huge challenge because, well, mostly because of radiation, of course, because we have our astronauts flying through space for 6 to 7 months. And, well, we have, as Cyprien explained, we have solar radiation, we have the cosmic background radiation. We will need to learn how to shield ourselves from those because the human reproductive system, so male as well as female, is extremely sensitive to radiation. And it's quite possible that astronauts will arrive on Mars and not be fertile anymore. If, in case they manage, also radiation on the surface of Mars is of course a huge problem. And embryos or fetuses inside during pregnancy are also extremely vulnerable to radiation. And of course a kid growing up is extremely vulnerable to radiation. And then there's also the fact that spaceflight changes hormones. Testosterone, for example, is in a lot of male astronauts very, very low in space. And that might be simply a reaction to stress, but it might also be something that's permanent. And how that would affect a boy growing up, for example, is something we simply don't know yet. Then there's also toxic components in the Martian soil that might have interactions with our thyroid hormones, which is also something we really need to work well if we want to grow up healthy. And then, of course, there's the question, a child born on Mars, or somebody who spends 3, 4, 5 years on Mars, whether they would have the possibility of ever returning to Earth, or whether we would basically ban them to Mars by making them grow up there. And this is, of course, because of the bones and the muscles and the heart, but it's also because of the immune system, because the immune system is a tiny bit like a muscle itself. The more you exercise it, the better it gets. And in a sterile environment, such as a spaceship or a space habitat on Mars, it would just not get a lot of training. And it's possible that it would never develop fully, and that somebody born there, returning to Earth, would simply not be able to survive because the immune system is not able to cope with, well, microbes coming in through the air. And with this, I believe, I give over to Cyprien again.
Okay, so if I get to talk properly, Carmen, humans are quite an unreliable piece of equipment, which begs the question, why don't we just send robots instead? And it's true that you don't need to feed robots, they don't need a pressurized compartment, they don't need oxygen, they don't need water, they might break but they won't die. And on top of that, they're much better at humans at some things, typically things which are highly repetitive and that are well defined and that were thought through before the robots left the Earth. But there are still things that humans are better at than robots. I mean, humans, for instance, have a much better mobility. If you look at Curiosity, for instance, since landing in 2012, it's been driving about 31 kilometers on the surface of Mars, which is impressive. I mean, it's quite an accomplishment to drive a machine over that distance on Mars while taking some measurements. But a human could do that much faster. And not only could they go much faster, but they could also go above some terrain that Curiosity could not roll over. Then humans are much better at dexterity. I mean, it's much easier to put something in a tube or to repair some equipment if you have hands. And humans are also much better at things that require intuition or that require improvisation. There's probably going to be a lot of that on Mars, if only because we're going to learn things by looking at something we didn't expect and try to investigate. And a robot could hardly do that. And it's quite easy to visualize if you imagine that you're on Mars and there is next to you a robot, that maybe will take a measurement and a sample, after some scientists on Earth, or a team of scientists, instructed it to do so. And if you compare that to one human who's just like walking around, looking, and is going to spot a site that looks interesting, maybe because the color is weird or because it has just the right amount of shade, and then he's going to go there and pick a rock and look underneath and take some measurements in the field, and if it's interesting, bring some rocks to the lab and to do some more analysis there, and then if they find something odd, then go back on site and do more. So a human could do much more and much faster. That being said, there is an argument for robot, which was brought in the book by Caroline Freycinet, and that I'm going to try to simplify without denaturating it, which has to do with the fact that sometimes the limiting factor is not data availability, but data analysis and interpretation. And Caroline gives this example of a measurement of mudstone taken by Curiosity in 2013, which is still giving some information. Or a more extreme example could be that of measurements taken from the Viking landers in the 70s, which still lead to the identification of new compounds today. And the reason for that, the reason why it takes so long, is that the data is very complex, so it takes a lot of highly skilled people to analyze it. And some people who want to do experiments on Earth, and that might require looking for analog samples, something which are analogous to the Martian samples. And then when they publish the data, then they will get feedback and maybe reinterpretations from the scientific community at large. And if the robot is still there, then maybe the robot can still make some additional measurements, maybe with different parameters. But an astronaut might be back on Earth and other astronauts may be on different areas of the planet. Now you might argue that robots could also bring back samples and analyze them on Earth 10 years later, and that's true. And I guess even the first missions to Mars could bring tens or even hundreds of kilograms of regolith, which is much more than a few hundred grams than a robotic sample return mission would bring. But because it takes so long to make sense of the data, it's possible that the rocks we're bringing back are not interesting. So one compromise, which Caroline mentioned, could be to send astronauts to areas that robots have identified as being interesting. And more generally, I think the robotic program and the human program are both necessary to, let's say, an optimal Mars exploration program, and that both should be developed jointly. Now, you might also argue that I'm neglecting an aspect of robots, which, if you're being cynical, you might argue are not shared by humans, which is that we expect robots to improve in the future. And that's true. But to paraphrase something that Charles Coquelle once said, there is a sense that humans are the most versatile and complex robots that we'll ever have access to. And even if that were not true, even if we develop robots which have all the operational capabilities of a human, I still think we should send humans to Mars. And that's because space exploration is not only about science. And the reason why so many people were fascinated by the Apollo moon landings is not only that they were excited about all this data we were about to collect. People were fascinated because they could see a human being on the moon telling them what it felt like to be there. And of course, a robot can hardly do that. I mean, a robot cannot tell you what it feels like to stand on a red planet on a watchable sunset, or to dance a tango in Martian gravity, or to get lost in thought and think of your loved ones very far away from you while watching a dust devil cross a barren landscape, or to stand next to Olympus Mons and wonder what the view is like from up there. And there is one more thing I would like to mention, which is that we're getting increasingly concerned about artificial intelligence, like ChatGPT, replacing humans for things we find meaningful. Writing, for instance. And I agree with that, that's a concern of mine. But it seems like we're willing to abandon to robots some of the most powerful human experiences. Exploration and adventure. And that I find a little bit saddening. This talk is almost over. There is just one topic I would like to touch upon, which is terraforming. So this idea that we can modify Mars to make it habitable, most mainly by changing the atmosphere. And there will be one chapter on that in the book, written by François. Unfortunately, we don't have that chapter yet, so I cannot tell you what François is going to tell us. But I will make an educated guess based on conversations we had and based on things that François said on other occasions. François, if you're watching this and I'm completely misrepresenting what you wanted to write, then please forgive me. Well, that being said, this would not have happened if you had sent your chapter in time. But so, terraforming. That's an idea which is not really new. I mean, you can find it in old science fiction books. But it really entered the scientific debate in 1991 with a paper published in Nature by 3 then young scientists at NASA Ames, which was called Making Mars Habitable. And that was relatively it was a well thought through paper. One of the hypotheses of which was that there was a lot of frozen carbon dioxide on Mars at the pole and in the regolith, in the interstices and adsorbed to the grains, and that by heating the planet we could release it, we could sublimate it and increase the atmosphere, the atmospheric pressure. And heating could be done in different ways. We could spread some dark powder on the ice caps, for instance, to make it absorb more solar energy. We could put some mirrors in orbit. We could send some hydrogen bomb to the poles, like Elon Musk suggested. We could, maybe more realistically, have some production plants for greenhouse gases, like chlorofluorocarbonates or perfluorocarbonates. And the author of that paper suggested that we could get about 1 bar of carbon dioxide in roughly a few hundreds or a few thousand years. And then once we have 1 bar of carbon dioxide, we can walk around on Mars with an oxygen mask and we can start seeding plants for the next stage of terraforming, which would be turning that carbon dioxide into oxygen. Now, we would also need some other gases, like nitrogen, for instance, so that the atmosphere is not too dangerous. But let's set that aside. And the authors said that it would take at least 100,000 years. And at that time, it did make sense. But since then, we've learned a lot about the Martian environment. And one of the things we've learned is that there is actually not so much carbon dioxide ice. There is quite little at the poles, and adsorbed to the grain is mostly water and not carbon dioxide. So even if we sublimated everything, all the frozen carbon dioxide on Mars, we'd not increase the atmospheric pressure by more than a few millibars. Now, another option, it seemed, could be to vaporize the carbonates on the surface. Because at some point in the Hurricane, we had a thick atmosphere, most likely of carbon dioxide mainly. We had liquid water, and in those conditions, when we have carbon dioxide dissolving in water on Earth, we form carbonates. So it was a reasonable expectation, but we found afterward there is actually not so much carbonate on the Martian surface. You might hear about carbonate-rich soils at G0, but actually not representative. We selected this site because there are carbonates. And in fact, if we vaporized all the carbonates on the Martian surface, and good luck with that, we'd probably not increase the atmosphere more than a few tens of millibars. Now, it's possible that there are reservoirs deep in the subsurface and that we're going to be able to access it in some time. But even then, it would take a lot of energy to vaporize them. And it's been calculated that to get a thick atmosphere, you would need the energy equivalent of a few millions hydrogen bombs to vaporize it all, or to vaporize it enough to have 1 bar carbon dioxide. And you would need to release that energy deep in the subsurface, so that sounds a bit challenging. Now there is one more option which was worth considering, which is bringing into the Martian atmosphere the gases that you need. And one way of doing that could be, it's been suggested, rerouting comets. But just in terms of mass, you would need about 1 million comets to get 1 bar. And even then, that would not be the gas composition you want. So all in all, with the technologies we know today, or that we can foresee, it seems impossible to terraform Mars. Of course, we cannot exclude that one day we'll have technologies that we didn't expect and that can enable us to do so. And then the next question will be whether or not we should do it. But that's a question for another time. Thank you for your attention.